This question is on uncertainty. It says the absolute uncertainty in some value A is 0.3 centimeters. The absolute uncertainty in another value B is plus or minus 0.07 centimeters. What is the absolute uncertainty in their sum? This could not be easier. Whenever you add two values together, you add their absolute uncertainties. In other words, the absolute uncertainty in the sum is equal to the sum of the individual uncertainties. So that's going to be 0.3 centimeters plus 0.07 centimeters. These are absolute uncertainties, so they have the units. So what do we get when we add these together? We get 0.37 centimeters. But we know we have to round absolute uncertainty, and we have to put the plus or minus. So that gives us plus or minus 0.4 centimeters as the answer. Here's another problem on uncertainty. It says the absolute uncertainty in a measurement A is plus or minus 0.06 seconds. The absolute uncertainty in another measurement B is plus or minus 0.08 seconds. These are clearly time measurements. What's the absolute uncertainty in their difference, B minus A? The rule is that whenever you subtract two quantities, you add their absolute uncertainties. In other words, the uncertainty, the absolute uncertainty in the difference is equal to the absolute uncertainty in B plus the absolute uncertainty in A. So clearly this right here on the left side is just a variable. You could call it x if you wanted. We're not distributing the triangle through or anything like that. You could just say that you could replace this instead if you wanted with absolute uncertainty and the difference, and say that that is equal to the sum of the individual absolute uncertainties. Okay then, so we plug in the absolute uncertainty in B, which is 0.08 seconds. We plug in the absolute uncertainty in A, which is 0.06 seconds. And what do we get as the absolute uncertainty in the difference? We get 0.14 seconds. But of course, we have to add our plus or minus, and we have to round every absolute uncertainty to 1 sig fig, and that gives us plus or minus 0.1 seconds is equal to the absolute uncertainty in the difference. Here's an uncertainty problem where we have to use the rules of propagation through multiplication and division. The problem says Q equals MC times delta T. The percentage uncertainty in Q is 5%. The percentage uncertainty in M is 1.9%. The percentage uncertainty in delta T is 3%. What's the percentage uncertainty in C? So the first thing we need to do is have an equation which isolates C. So if you look at this, if we divide both sides by M and delta T, then we get C equals Q over M delta T. We'll study what this equation means later in the semester. So if we have this equation, then we know that the percentage uncertainty in C is equal to the percentage uncertainty in Q plus the percent uncertainty in M plus the percentage uncertainty in delta T. How do we know that? Because the rule, the general propagation rule, is that whenever you have two things, two measurements that are being multiplied or divided, you always add together the percentage uncertainties, not the absolute uncertainties. So what do we have here? We could replace the percentage uncertainty in Q with 5%. We know the percentage uncertainty in M, it's 1.9. We know the percentage uncertainty in delta T. It's 3%. So adding these up, we get, 9.9%. And a general rule, a good way to round is whenever the percentage uncertainty is 2% or higher, round to 2 places, or just round to the nearest whole number. So that becomes 10%. And that's our answer. Here's another uncertainty question which involves multiplication and division. It says the percentage uncertainty in v, the speed, is 1.4. You don't need to list the givens for these kinds of questions, but I will go ahead and do it. The percentage uncertainty in v is 1.4%. The percentage uncertainty in d is 3%. My percent signs sure are ugly. Let's try that again. Percent. Good. What is the percentage uncertainty in the time taken to travel the distance at that speed? So, to find the percentage uncertainty in time, we need an equation for time. We know that speed is distance over time. So if we isolate time, we get distance over speed. And that tells us speed. We are dividing two measurements. And whenever we divide two measurements, we add together the percentage uncertainties, not the absolute uncertainties. So the percentage uncertainty in time, t, is equal to the percentage uncertainty in distance plus the percentage uncertainty in speed. We know what those values are. They're 3% and 1.4%. Adding together, we get 4.4%, which is about equal to 4%. Since it's bigger than 2%, we round to the nearest whole number. Here's a question on percentage uncertainty which involves exponentiation. The percentage uncertainty in mass is 8%. What's the percentage uncertainty in mass to the power of 1.4? So here's how we do this question. And again, we don't need to list the givens, but I will just for clarity. The percentage uncertainty in mass is 8%. The percentage uncertainty in mass to the 1.4 is the unknown. The rule for exponentiation is whenever you take a measurement, which is uncertain, like mass, and you raise it to some power, you always multiply the power by the percentage uncertainty in the measurement. Here's the fancy way, that's a fancy way of saying what I'm about to put onto the page. The percent uncertainty in mass to the 1.4 is equal to the power 1.4 times the percent uncertainty in the mass. In other words, it's 1.4 times 8%. And when we multiply that out, what do we get? We get, I think it comes to about 11.2%, which rounds to the nearest whole number, 11%. And that's the percentage uncertainty in mass to the power of 1.4. So again, notice this here is my variable. I could have just as easily not written a variable, but instead I could have written percentage uncertainty in mass to the 1.4. Here's another problem involving percentage uncertainty and exponentiation. There are certain types of problems that involve, like, they tell you something about the radius, and then they ask you something about the uncertainty in the volume or the surface area. And there's a trick with these. So here's the trick. I'm going to break the question into two parts. The first part is this. The percentage uncertainty in the radius of a sphere is 2%. What is the percentage uncertainty in the radius cubed? This is easy. Whenever you take a measurement like r and you exponentiate, like raise it to the power of 3, the way you find the new percentage uncertainty is you multiply the power 3 by the percent uncertainty in r. So The percent uncertainty in r to the third is just going to be 3 times the regular old percent uncertainty in plain old r. And what's that going to be? It's 3 times 2%. That gives us 6%, plus or minus 6%. So that's the percentage uncertainty in r cubed, which is what they asked us to find. Oops. Now what I want to look at, what's the percentage uncertainty in the volume of the sphere? Well, volume, you may know, of a sphere, but it doesn't actually matter if you know this equation. Volume is 4/3 pi r cubed. And that means we have two things being multiplied, 4/3 pi and r cubed. So whenever you multiply two things, like 4/3 pi and r cubed, you add together the percent uncertainties. Like that, to get the percent uncertainty in the new quantity. But the percent uncertainty in 4/3 pi, this is 0. There's no uncertainty at all. We know exactly what 4 pi over 3 is. So this whole thing is 0. And all we're left with is the percent uncertainty in r cubed, which is 6%. So it doesn't matter if you know what the equation is for volume. It doesn't matter if you know that it's 4 pi over 3. It doesn't, it could have just as easily been 4 pi, and 4 pi would still have no uncertainty, and you would still get 6%. So all you need to know to find the percentage uncertainty in the volume, all you need to know is that volume is 3 dimensions, which means it has to be r times r times r. In other words, the percent uncertainty in the volume will always equal the percent uncertainty in r cubed. Here's another problem involving percentage uncertainty, and it's a problem that uses the radius of a sphere. The question says the percentage uncertainty in the radius of a sphere is 7%. What's the percentage uncertainty in the surface area of the sphere? So I'm going to use the same trick that I showed you in the last question, the last problem. I'm going to find the percentage uncertainty in r squared. And that's simply 2 times the percentage uncertainty in r. When you take something that's uncertain, like r, and you raise it to a power, you find the new percentage uncertainty by multiplying that power 2 by the original measurement. In other words, if you exponentiate a measurement, you must multiply that measurement's percentage uncertainty by the power to get the new uncertainty. Good. So we can simply and quickly solve for the percentage uncertainty in r squared. It's 2 times 7%, and that gets 14%. So the percentage uncertainty in r squared, which is what we were asked to find, is simply, that's not what we were asked to find, is 14%. Except that if the percentage uncertainty in r squared is 14, then the percentage uncertainty in the surface area is also 14%. Here's why. You may not know this, but the surface area equation for a sphere is 4 pi r squared. Now, if you want to know what's the percentage uncertainty in the surface area, it's going to be equal to the percentage uncertainty in 4 pi plus percentage uncertainty in r squared. And of course, 4 pi is perfectly certain. It has no uncertainty, so this first term is 0. And the second term, we just found 14%. 0 plus 14% is 14%. And the beautiful thing about this is that you might have been wrong about the surface area equation. Maybe you thought it wasn't 4 pi, maybe you thought it was 4 pi over 3, or 2 pi. You may not have known, but you don't need to know, because all of these things, 4 pi, 4/3 pi, and 2 pi, they all are perfectly certain, and this will still be 0, and we'll still get 14%. So that's our answer, 14%.